So, we're going to finish off chapter 3 today. Your chapter 3 homework is due on Wednesday, which is also when you will have the quiz on chapter 3. We have a lab today, which I'll have to go up and print because I've been busy grading. And the exam is graded. Your scores are up on Blackboard. You can pick them up here after class. I also have the labs from last week. These are the stats. So the average score was around 125.9. And these are the stats for the various. I think that's the wrong number in for range. Yes, I definitely put the wrong number in for range. There. I'll have to recalculate that if I was getting there. But there's the range in points. I don't know where exactly I got that number, but I think I copied the wrong number in from my Excel sheet. You can get it by dividing the range in points by 1.5. So it's something in the 20-ish range per percent range. Yeah, so those are the average, the median, the standard deviation, things like that. So generally people did okay. The average was in the 80s percent-wise. I haven't graded your quizzes yet, as I've been grading things in the order that I did them. So continuing on, momentum. Oh, and your midterm grades will be coming out during spring break. So momentum, linear momentum is mass times velocity. It's another way to understand inertia, that tendency of things to keep moving. And if we have a system of masses, the linear momentum is the sum of all the individual momentum vectors. And one of the things about momentum is conserved. Final momentum is equal to initial momentum as long as there are no external forces. Where, the capital P here is the sum of all the individual momentum vectors, which means for something like a collision, momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. Because for a collision, you could generally go, collisions happen so fast that we don't need to worry about external forces. So the law of conservation of momentum is that the total linear momentum of an isolated system remains the same if there are no external unbalanced forces acting on the system. Linear momentum is conserved as long as there are no external unbalanced forces. It does not change with time. So here is an example. The man jumps forward, gaining momentum in this direction. So the boat has to gain an equal momentum in the opposite direction, so the total momentum remains 0. This is a consequence of a combination of Newton's second law and Newton's third law. You could derive the relationship for momentum and conservation of momentum from Newton's laws. Every force equals mass times acceleration, and every force is an equal opposite force between two objects. And you can figure out that for any two objects, their forces acting on each other, momentum is conserved. You don't need to know this derivation. This is just how you get it. So here's an example problem. So general rule for momentum. Momentum is mass times velocity, and it is a vector. It has a direction. So here we have a 3-gram bullet traveling at 333 meters per second. What is its momentum? And do remember that momentum should be in kilogram meters per second. So make sure to do the correct conversions. Oh, so momentum is mass times velocity. 3 grams times 333 meters per second is 0.003 kilograms times 333 meters per second, which is 0.999 kilogram meters per second. Just a little less than 1 kilogram meter per second. Here we have a 4.5 kilogram ball. It has a momentum of 900 kilogram meters per second. What is its velocity? Well, this is also fairly straightforward. Momentum is mass times velocity. So velocity is going to be momentum divided by mass, which is a common calculation you'll need to do because often you'll know, say, the total momentum. You'll figure out what the momentum of another thing should be. You want to figure out how fast it's traveling, you divide by mass. So 900 kilogram meters per second divided by 4.5 kilograms gives you 200 meters per second. Which is going very fast. So linear momentum is mass times velocity. Conservation of momentum is initial mass equals, initial momentum equals final momentum. The momentums have to cancel out. Here's an example. Here we have two masses starting at rest on a frictionless surface. And there's a spring in between them. And they're tied together with a string. When the string is broken, the two masses fly apart. And the velocity of the first mass, which is 1 kilogram, is 1.8 meters per second in the positive direction. So what is the velocity of the second mass? That's what we want to find. So we're given mass 1 is 1 kilogram, mass 2 is 2 kilograms. And velocity 1 is 1.8 meters per second. Velocity 2 is unknown. We know the initial momentum equals 0. That equals the final momentum, which is mass 1, velocity 1 plus mass 2, velocity 2. This is momentum 1, this is momentum 2. So minus mass 1, velocity 1 equals mass 1, velocity 1 equals minus mass 2, velocity 2. We want velocity 2. Velocity 2 ends up equaling minus mass 1, velocity 1 over mass 2, which is minus mass 1 is 1.0 kilograms. Velocity 1 is 1.8 meters per second. Mass 2 is 2.0 kilograms. So velocity 2 is minus 0.9 meters per second. Velocity 2 ends up equaling minus mass 1 v1 over mass 2 minus 0.90 meters per second. Sort of the general momentum, when you approach momentum problems, you figure out the total momentum. You can then usually figure out the individual momentums because you know what they have to add up to, and then solve. And if the initial momentum is 0, then mass 1 times velocity 1 equals minus mass 2 times velocity. Now, an example of conservation of momentum is jet propulsion. To demonstrate, here we have a balloon. We fling air out the back, and because momentum has to be conserved, the balloon moves forward, or whatever direction it ends up going, and opposite the direction that air is flung out the back. So in a rocket, the exhaust gas molecules have small mass but very large velocity. The rocket has a larger mass and thus a large mass and a smaller velocity, but momentum is conserved. So here, if you have a system that consists of a 1 kilogram mass with a velocity of 3.5 meters per second and a 2 kilogram mass with a velocity minus 1.75 meters per second, what's the total momentum of the system? And after the two masses collide, what is the total momentum of the system? So remember, momentum is mass times velocity, but it's a vector, so you do have to keep track of signs. So this is fairly straightforward. Momentum is mass times velocity. Total momentum is momentum one plus momentum two. So mass one times velocity one plus mass two times velocity two. So 1 kilogram times 3.5 meters per second plus 2 kilograms times negative 1.75 meters per second. So you see, it happens to be 3.5 kilogram meters per second minus plus negative 3.5 kilogram meters per second. So the total momentum is actually 0. And then after they collide, the total momentum is still 0, doesn't change. So this is a case, if these two collided and stuck together, they wouldn't be moving. Here, we have a 1,000 kilogram cannon at rest, fires a 4.5 kilogram ball at 300 meters per second. What's the velocity of the cannon after the ball is fired? So this is basically recoil. The ball goes forward, the cannon goes backwards. So I'll let you try and work this out. Momentum is mass times velocity. Initial momentum is momentum one plus momentum two. So mass one times velocity one initial plus mass two times velocity two initial. And in this case, is zero. Because everything's at rest. 1,000 times zero plus 4.5 times zero. That's zero. Initial momentum equals final momentum. Momentum initial plus momentum final equals mass one times velocity one final plus mass two times velocity two final. So zero equals mass one times velocity one final plus mass two times velocity two final. We are interested in the mass of the cannon, which we'll call mass one, and the velocity of the cannon. The velocity one final is mass two times velocity two final over mass one. So that's going to be 4.5 kilograms times 300 meters per second over 1,000 kilograms, all with a minus sign. And that comes out to minus 1.35 meters per second. While the cannonball is moving quite fast, the cannon is moving much slower. So here, two masses starting at rest of 3 kilograms, mass one, which is 3 kilograms, and mass two, which is 12 kilograms. They're torn apart by a spring. After they separate, mass one has a velocity of minus 4 meters per second. What is the velocity of mass two? This is again a very similar problem. So momentum is mass times velocity. Once again, our starting momentum is zero because everything starts at rest. So once again, zero equals mass one times velocity one final plus mass two times velocity two final. We're looking for velocity two. So mass two times velocity two final equals minus mass one times velocity one final. So velocity two final equals minus mass one times velocity one final over mass two, or momentum two over mass two. Actually, that's minus momentum one over mass two. That's a typo. So velocity 2 final is minus 3 times minus 4 meters per second over 12 kilograms, which ends up being minus times minus 12 over 12, which comes out to 1 meter per second. Negative 12, which is positive 12 divided by 12, which is equal to that. Okay, let's start talking about rotation. So torque is the twisting effect caused by one or more forces. This is the rotational equivalent of force. And as we've learned, linear momentum of a system can be changed by introducing an external unbalanced force. Similarly, for rotation, angular momentum can be changed by an external unbalanced torque. The torque is a twisting action that produces rotational motion or a change in rotational motion. And it is proportional to the force times the lever arm. So it varies with the length of the lever arm. So force times radius. So to increase torque, you could either increase the force you're applying or use a longer lever arm to apply that force. So here the same force with a short wrench and a long wrench. Because the long wrench has twice the lever arm, it will have twice the torque. This is why people use like cheater bars to extend wrenches to tighten things more. So I don't need these calculations anymore. Torque equals force times radius. So which has more torque? 4 newtons on a lever arm of 0.5 meter or 5 newtons on a lever arm of 0.2 meters? Which of these two has more torque? 4 newtons on 0.5 meter or 5 newtons on 0.2 meters? Any guesses? Okay. Well, torque is force times radius. So our first one, force 1 times radius 1, 4 newtons times 0.5 meters is 2 newton meters. And you'll see the units for torque are newton meters. You'll see that in car advertisements. In imperial units, they are in foot-pounds. And here we have our second torque. 5 newtons times 0.2 meters is 1 newton meter. So the first torque is twice the second torque. The torque 1 is bigger than torque 2. Another thing with rotation is something called the law of conservation of angular momentum. There is an equivalent of momentum for rotation, If there's no external unbalanced torque, a force around an axis acting on an object, then angular momentum is conserved. This concerns objects that go in paths around a fixed point, for example, a satellite orbiting the Earth. And I believe I have a demonstration of this coming up, so let me just make sure I have the sound set up right. So angular momentum, L, for a point object is mass times velocity or speed times radius. Distance to the center of motion. And for something like a comet or something orbiting, angular momentum is conserved as it orbits. You can have L1 over L2. So one of the things that can happen with angular momentum is that you can have one object, but you can change the radius. And because of that, the velocity changes, while the angular momentum remains constant. So you'll often get mass 1, velocity 1 times radius 1 equals mass 2, velocity 2 times radius 2. But usually, very commonly, mass 1 equals mass 2 because it's the same object. The mass is constant. So as radius changes, so must the velocity. When radius decreases, velocity needs to increase. So when something is orbiting the sun, for example, it's faster when it's close to the sun and slower when it's further from the sun because it has to conserve angular momentum. And when mass is constant, radius 1 times velocity 1 equals radius 2 times velocity 2. So in our solar system, planets' orbital paths are slightly elliptical. Therefore, both radius and velocity will slightly vary during the complete orbit. So the Earth is closest to the sun in January and furthest from the sun in July. It's traveling fastest around the sun in January and slowest in July. But this is much more dramatic for comets. You might notice that I mentioned that the Earth is closest to the sun in the winter. That's because the change in distance is so small as to have no real effect on the temperature. But it has to do with, but the seasons are caused by the tilt of the Earth. So we're in the winter right now. That's because the northern hemisphere is currently facing away, tilted away from the sun, and the southern hemisphere has summer. So here, but this is much more dramatic with comets, which have much more elliptical orbits. There's a bigger difference between the close and far. So a comet, at its furthest point from the sun, is 900 million miles away, traveling at 6,000 miles per hour. At its closest point from the sun, it's only 30 million miles away. What is its speed then? So mass 1 times velocity 1 times radius 1 equals mass 2 times velocity 2 times radius 2. Mass 1 equals mass 2, so they cancel. So velocity 1 equals velocity 2 times radius 2 over radius 1. So we have 6 times 10 to the third miles an hour, 6,000 miles an hour, times 900 times 10 to the 6 miles, 900 million miles, divided by 30 times 10 to the 6 miles. Miles cancel, you can cancel the 10 to the 6. 900 divided by 30 is 30. So 6 times 30 is 180. So this is 1.8 times 10 to the 5 miles per hour, or 180,000 miles per hour. Another example of conservation of angular momentum is the rotors on large helicopters. On large helicopters, you have rotors that rotate in opposite directions. That's to conserve angular momentum, because otherwise, if you had one going one way, or if you just had one rotor spinning, the helicopter would spin the other way. This is also why helicopters have that little propeller on their tail. That's to do the same thing. It's to create a torque that balances out the torque caused by the runners. And the classic example is a figure skater. A figure skater in a jump starts with their arms and legs out, and then they pull their arms and legs in and spin faster because the average radial distance of their mass decreases. And I will demonstrate this. So start with my mass outstretched. I'll apply some torque with my foot to get spinning. And then as you can see, when I pull the mass in, I speed up. When I let the mass out, I slow down. Speed up, slow down. And now I stop before my inner rear repels on. And now the world is spinning. Because unlike a figure skater, I am not able to execute the proper technique to reduce that. Oh. So, if you have a 0.35 kilogram mass spinning on a 0.5 meter string, traveling at 5 meters per second, what is its angular momentum? Oh, angular momentum is mass times velocity times radius. So 0.35 kilograms times 5 meters per second times 0.5 meters, which is 0.875 kilogram meters squared per second. Here we have a spinning mass, spinning half-kilogram mass on a string that has a speed of 4.5 meters per second and an angular momentum of 0.9 kilogram meters squared per second. How long is the string? Oh, angular momentum is mass times velocity times radius. The radius is angular momentum divided by mass times velocity. So 9 kilogram meters per second squared over 0.5 kilograms times 4.5 meters per second, which comes out to 0.4 meters. So here, I'm spinning a 0.1 kilogram mass on a 0.3 meter long string. The mass travels at 3.6 meters per second. If I short the string to only 0.2 meters, how fast will the mass move? And there's the formula you get. Oh. Angular momentum equals mass times velocity times radius. Angular momentum is conserved, so mass 1, velocity 1 times radius 1 equals mass 2, velocity 2 times radius 2. But mass 1 and mass 2 are going to be the same object. Here I just plug them in. There's 0.1 kilograms times 0.36 meters per second times 0.3 meters is 0.1 kilograms times V2 times 0.2 meters. The 0.1 kilograms cancel, and you just get 3.6 meters per second times 0.3 meters divided by 0.2 meters. Or you could do it like this. The final velocity you get is 5.4 meters per second. You can also do 3.6 times 0.3 divided by 0.2, which also gives you 5.4 meters per second. And here we have the 3,000 kilogram satellite of Moon with an elliptical orbit. Its closest to Moon travels at 3.3 times 10 to the 5th meters per second, and is 2 times 10 to the 7th meters from the center of Moon. At its furthest from Moon, the satellite is 5 times 10 to the 8th meters away from Moon. How fast is it traveling there? So this is a very similar problem. And remember, the mass will cancel out. Oh, the momentum is mass times velocity times radius. Mass 1 times velocity 1 times radius 1 equals mass 2 times velocity 2 times radius 2. But mass 1 equals mass 2. So velocity 1 times radius 1 equals velocity 2 times radius 2. Thus, velocity 2 will equal velocity 1 times radius 1 over radius 2. So that's 3 times 10 to the 5th meters per second times 2 times 10 to the 7th meters divided by 5 times 10 to the 8th meters. Which comes out as 1.2 times 10 to the 4th meters per second, or 12,000 meters per second. If you're doing this by hand, you could say 3 times 2 is 6. 5 plus 7 is 12. Over 5 times 10 to the 8th. 6 over 5 is 1.2. 12 minus 8 is 10 to the 4th. Or you could, enter it into your calculator. So that's the end of chapter 3. So here are some important equations. Force equals mass times acceleration. That's Newton's second law. This also leads to weight. Weight is mass times the acceleration due to gravity, g. Newton's third law is the force of object 1. The force on object 1 from object 2 equals the force on object is equal to minus the force on object 2 from object 1. The universal law of gravitation, the gravitational force between two objects, is big G times mass of object 1 times mass of object 2 over the distance between them squared. Big G is this constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Little g, the acceleration due to gravity, can be calculated from big G times the mass of the Earth over the radius of the Earth. Momentum is mass times velocity. Conservation of momentum, so final momentum equals initial momentum. That's particularly true in collisions or anywhere where there aren't external forces. Angular momentum is mass times velocity times radius. So conservation of angular momentum, mass 1 times velocity 1 times radius 1 equals mass 2 times velocity 2 times radius 2. And torque is force times radius. So here is if momentum total is 0. I'm going to stop sharing and end the meeting.